Hello guys, welcome to lesson 2 in our thermodynamics unit. We're going to look at entropy and free energy. So thermodynamics, thermo meaning energy and heat energy specifically. Thermochemistry was just dealing with delta H, was enthalpy and heat and Q and work. For thermodynamics, we're adding dynamics, right? That means that systems can change. That's what dynamic means. It's ever changing, it's not staying the same. We have two new words that we're adding on to this unit is entropy and free energy. Entropy is represented by the letter S, or delta S, and energy is represented by the letter G. So free energy is not the same as energy. It's a little bit different. I'll have to explain it down below. And delta H was enthalpy. So that was our previous lesson, our unit that we learned in first semester. So we're adding on entropy, or S, and free energy, G. And so standard state, we need to define a couple things first. Standard state is saying that thermodynamic quantities are generally reported at standard state, and at which all aqueous substances in the reactants and the products are at 1 molarity concentration, and gaseous substances have a partial pressure of 1 bar, or approximately 1 atm, or atmosphere. It's usually denoted at 25 degrees Celsius, or 298 Kelvin, and in other words, the reversible reaction is Q equals 1. And those are usually denoted by the little degree symbol. In summary, let me put that in a little bit better English for you, is that at standard state, it's basically STP, right? Standard temperature, pressure, all of that stuff. So standard state is something that occurs at general experimental conditions, right? And remember that STP is always 25 degrees Celsius or 298 Kelvin. It's usually at 1 atmosphere, so standard temperature, standard pressure. For aqueous substances, the standard molarity will always be 1 molarity. And then Q equals 1. Remember that Q or K is just products over reactants. And so if the products and the reactants are the same, it will equal 1, right? They will equal each other. So that means that you have the same amount of products, you have the same amount of reactants. So when you divide them, it will just equal 1. And so those standard states are usually denoted by that little symbol right there, that little degree symbol. And so if we have enthalpy, delta H, standard state, or S, entropy at standard state, or delta G, or E. So quick difference between delta G is free energy, delta E is the internal energy. So go back to the first lesson, right? Energy, internal energy was Q plus W, so heat plus work, whereas delta G is free energy, and they're slightly different. All right, so going down to entropy. Entropy, or S, is a measure of the dispersion of matter and energy. It's just a fancy way to say that it is chaos. Chaos, there we go. Right, so everything in the universe tends to drive towards entropy. It tends to drive towards chaos. Things get more and more and more complicated. They never get simpler. And so everything is always becoming more entropatic. I don't know if that's a word, but I'm using it, right? So everything's increasing in entropy, it's increasing in chaos. Think of you cleaning your room, your bedroom. You clean your room, it looks beautiful for a day or two. By the end of the week, it is complete chaos again, right? And it stays like that. It likes to stay as a kind of cluttered mess. And so that is chaos. Everything tends towards chaos, everything tends towards entropy. And it takes a lot of work to make it not chaotic, right? It takes a lot of work to keep your room organized, to keep your room cleaned on a day-to-day basis. It's much easier to just let it run amok. So you can describe entropy as the number of arrangements of particles. So we can increase the particles, we can increase the complexity of the arrangement of particles, and it's also the disorder of a system. It has units of joules per mole Kelvin. Be careful with this because delta H, remember, usually had units of kilojoules per mole. And so if you have to add these two, which you will have to add these two later on, make sure that you either are both in joules or you're both in kilojoules. That's a common mistake. And the other thing to notice for this one is that you have Kelvin, right? So that means we need to multiply it by a temperature in order to get them into joules per mole or into kilojoules per mole. Right, moving down, the absolute entropy, or S, describes the entropy of 1 mole of a substance and can usually be looked up. More complex substances have larger values of S. So the more complex you are, the greater your entropy is. That makes sense. We are typically more concerned about the entropy change, or the delta S, of a process. If it's positive, entropy increases. If it's negative, entropy decreases, right? So positive, increasing entropy, more disorderly. Negative, decreasing entropy, less disorderly, right? So for this one, we tend to favor things that are positive delta S. But then remember, for enthalpy, delta H, we tended to favor things that were negative because that was exothermic, it was releasing energy, right? So positive is favored here, negative was favored for delta H. The value of delta S of a reaction can be found in two different ways. Products minus reactants, which is the exact same way as you find delta H, right? If you go back to lesson 11.1 and you look at delta H, the example 3b, that was products minus reactants. Delta S can be found the exact same way. You just have to be given the numbers, plug them in. The other way is Hess's law, and Hess's law is also the exact same way as delta H. Go back to example 3 from our previous lesson, letter C, so 3C. Exact same way. So I'm not going to show you guys how to do that. You know how to do it already. We're just replacing it with enthalpy with entropy. Increasing entropy. There's a couple ways that you can increase entropy. So increasing chaos. You can increase entropy of a system in the following ways, right? We can increase it by increasing the temperature of a system, the volume of a system, the moles of substances, or the number of substances. Right, so if you increase the temperature, there's more motion, more entropy, more chaos. You increase the volume of a gas, there's more gas, more chaos. Increase the moles or the number of substances, right? More things that you have, there's more collisions, there's more chaos around, right? Think of the population of humans, a couple billion to now almost 8 billion. There's a lot more chaos, a lot more war in the world, right? There's more entropy. Another thing is looking from solids to liquids to gases. Right, ordered is solid, very structured, all the way to a liquid, which is disordered, to a gas, which is extremely disordered. They're just bouncing around, looking around, bouncing off of each other and walls and stuff. And then the last way is by changing from a pure substance to a mixture. So something that's solid and then making it aqueous, right? So solid to aqueous. I'm going to skip example 1 for now. I'm going to go down to Gibbs free energy. And there's two ideas that we need to look at for Gibbs free energy, which I will describe in a later video because I want to keep these videos very short. But Gibbs free energy, the main idea behind that, the reason it's called Gibbs free energy is because it's named after Josiah Willard Gibbs, who was an American scientist. He died in 1903, right? So his work was mainly in the 1800s. So it was free energy, Gibbs free energy was named after him, which is why we use the letter G